Okay, so here we have a racing car that accelerates uniformly from rest, and then it travels to marker 4, and that marker 4, its final speed or final velocity, if you want, is 100 kilometers per hour here to the left, and then it wants us to find out where is the car when it was moving at 70 kilometers per hour. Okay, so let's go ahead and identify a few things here. Here, the initial speed or the initial final speed is given to us as 100 kilometers per hour. So I'm just going to label that where marker 4 is because it said so. And then that is the distance that it traveled by the time it reaches this particular final speed of 100 kilometers per hour. Well, it wants us to find where is the car when it was moving at 7 kilometers per hour. So just using common sense, it's us off somewhere between the start and M4, right? Because 70 is greater than 0 kilometers per hour, but less than 100 kilometers per hour. So here are your answer choices: A, B, C, D, and E. Let's go and crack this out. So to do so, I'm just going to use this particular kinematics function that requires no time, only because the problem gives me two final speeds to play with, and it also gives me the distance, aka marker 4 here. All right, so I'm going to go ahead and use a function that it does not involve time. So I'm just going to set this up. 1 on the left side of my chart here, I'm just going to call that VF. VF, once again, being the initial condition given to us here as 100 kilometers per hour. Well, the second condition is that the final velocity is now 70 kilometers per hour, right, which is less than 100. So how do I know what this ratio is? So to do it, I'm just going to take the initial condition divided by the second condition divided by the initial condition. So I'm just going to say 70 divided by 100, which is 0.7. Well, 0.7 of what? 0.7 of the original final velocity, right? So 70 is 0.7 of 100, which makes sense. All right, so make sure when you do this particular ratio that you put the number correctly in the numerator and the denominator. Otherwise, you can't screw up your board. All right. So how's this value useful? How's this 0.7 useful? I can say that the second final velocity is just zero point 0.7 of VF, right? I know it's at 70, but I like to do these types of problem using just a coefficient like a multiplier, okay? So the original is 100, the second is 70, which makes sense. 0.7 times 100 is 70. So I'm just going to go ahead and use this 0.7 in my work. So here, generically, I'm just going to write this kinematics function again, but I'm going to cancel out VI because VI is 0, so I'm just going to simplify that. So the final velocity in the initial condition here is just VF squared equals 2A. Well, instead of delta x, I'm just going to replace it with M4 because it's marker 4, right? So you can call this distance whatever you want. I'm just going to call it marker 4 just because the problem has it already dictated for us. Now, I'm just going to stop there. So as you practice this problem, you just have to know where to stop, all right? Here, I'm just going to apply the same physics function again on the right side. So really, I'm just doing the same physics function twice, right? And just pull out what's constant and things will cancel out. I'm going to cancel VI out. Well, here's VF on this left side, right? I do want to remind you that VF here is not the same as VF here, right? Over here, VF was 100. Over here, VF is 70. So I can express this VF as VF new now, quote unquote new, right? Because it is the second condition, a square, equals 2A. And then what is this delta x? Well, I don't know. That's what we're trying to figure out, right? Where is it when it reaches a speed of 7 kilometers per hour? So instead of calling it delta x, I'll just call it delta x new. So if you like the subscript new, use it. If you don't, discard it, call it 1, 2, whatever you want, okay? So, but what is this VF new? Well, up here when I did my work, I took the second scenario, which is the new VF, divided by the original, which is 100. So I can say this VF new is just 0.7 of VF. Okay, and this VF here in parentheses is the VF over here where the cursor is, right? So you just have to make sure you're just doing a comparison before and after. All right, so make sure when you get to here though, use parentheses, because folks who don't use parentheses, you're gonna get sloppy here. So you have to actually distribute this exponent 2 to the 0.7 and the VF. So I just made a note for you here, distribute the exponent, because otherwise you goof. All right, so 0.7 squared is 0.49, VF squared is just VF. On the right side, nothing has changed, I carry everything down. But once again, if you've seen my other videos, I just set up this, left and right side and just kind of let the function, guide itself. Here's VF squared on the left side, which is equal to 2AM4. So over here, I have a VF squared right here. Well, instead of saying VF squared, I can substitute it out. So I'll say 0.49. So instead of VF squared, I can make a true statement that says 2AM4, right? So I'm just going to substitute the information on the left side of the chart into the right side. So VF squared disappear, and that got substituted for 2am4. Well, as you can see here, there's a 2 there, there's a 2 there, that cancels out, there's an A that cancels out. So therefore, if you solve for x new is just 0.49m4. Well, so what's the answer then, right? Well, here's the start, and it goes to m4. 0.49 is about halfway, right? Halfway of the total thing. So it's just right before m2. So I'm going to go ahead and draw you a little arrow there from the start. But you notice here my arrow just kind of finishes just right before m2. I know it says 0.49, which is almost 0.5. So I drew it a little shorter just to make a point there. So therefore, I quite didn't hit marker 2 yet. So I'm just going to say that my answer is going to be between M1 and M2. Like it's almost at M2, but not quite. Okay, so that's the answer for this one. All right, let's do another one. So here, same diagram, but I just tweaked it a little bit. All right, it says like racing car accelerates uniformly again. The spacings are equal distances again. But here it's a little different because it says the car passes marker 1. Here's marker 1 in a time of 3 seconds. So it says where on the track is the car 4.8 seconds later. Well, so I'll just label things here. So 3 seconds is my initial condition, right? 4.8 seconds is my second condition. So here's t is equal to 0. That's where the car starts. And here is the first distance travel. Well, how much time did it take for this right here to happen, right? It says it takes 3 seconds to reach marker 1. So I'm just going to call that t. I know the problem gives you 3 seconds, but I'm just going to call that t being 3 seconds. So why do I do this? I like it in terms of variables because things will cancel out, okay? But it's up to you. So here, unlike the last example, here I'm going to use my displacement function. Why? Because it gives me a distance, aka marker 1, and it also gives me 2 times constraint to compare, right? So therefore, I'm just going to set it up. Here's t. And well, what goes on the right side here, right? T is just 3 seconds because that's the initial condition given. Well, I'm just going to use the same strategy I did last one. I'm going to take the second condition divided by the first condition. So here, 4.8 divided by 3 is 1.6. So 4.8 to me is 1.6 times the original time, whatever it is. Here it just happens to be 3 seconds. So the strategy, I like it. It just prevents me from plugging a bunch of numbers, that just makes my work longer, okay? So if you understood why this left side is t, that's the initial condition, which is 3 seconds. On the right side, it's 1.6 t because if you plug in t being 3, you will get 4.8, which makes sense, right? So I'm just going to set up my displacement function here. I'm going to cancel vi out because it starts at 0. I'm going to simplify this down. Well, what the heck is delta x1 for this particular problem? Well, delta x is just m1 because it says it passes marker 1 after 3 seconds. All right, so everything else on the right side stays the same. So I'm just going to apply again the same function again, except I'm going to cross vi out because it starts at 0. But instead of delta x, I'll just call it delta x, new, right? We know that it's going to travel farther because it's 4.8 seconds down the road. So it's covering more distance, but how much more, right? So on the right side, instead of t, I'm just going to call it t new, right? Because on the left side is 3 seconds, on the right side is 4.8 seconds. So I'll just call this the new time. So I'm going to keep x new the same. On the right side, though, the 1/2 gets carried down. A is a constant, so it doesn't have any subscripts here because it stays the same for both scenarios. So instead of t new, I'm just going to substitute out t new for 1.6 t, right? So if you understood how I got the 1.6 coefficient, I just did that here, 1.6 t, whatever t is. Again, I know it's 3 seconds for this one, but you can use this strategy for any t. T can be 6, t can be 5 seconds, t can be 20 seconds. It still doesn't matter. Just simplify these statements down to just a coefficient and it will make your life super easy to do, okay? So that's where the 1.6 come from, 1.6t. Well, once again, distribute this exponent to 1.6 and t. So if you distribute correctly, 1.6 squared is going to be 2.56. The t, once again, is square. So as you can see here on the left side, m1 is, right, 1/2 a t squared. Here I have 1/2 a 2.56 t squared. But really the only difference here is this 2.6 coefficient. So I'm just going to pull that out front, okay? So it would just be 2.56. Instead of saying 1/2 times a times t squared, I know that is m1, okay? So there it is. So, well, in 4.8 seconds, how far did it go, right? It went 2.56 times m1. So from my cursor to start as m1, that's 1. And then from here to here, that's another one. That's 2. And then from here to here, that's about half. Okay, it says 2.56. So right about here is where the car will be. Okay, so the answer for this one is going to be between M2 and M3. Okay, all right, I hope that helps. Stay nerdy, don't be wired.